Today we're going to talk about the area of a region that's between two curves. We've already talked about finding an area between one curve and the x-axis, but we're going to take it a step further. So if I wanted to find, use the diagram below to write an expression that could be used to find the area between the graphs of f and g on the interval between a and b. So basically what I'm trying to do is I am trying to find the area of that region right there. Okay, so someone back there in the back is already telling me how to do it. What do I need to do? Okay, so I need to take the integral of f from a to b. And that would actually give me that whole part right there, integral of f of x. And then if I were to subtract the integral of g on that same interval, then I would be left with that purple part right there. Good. Now, two integrals is always kind of messy. So the integral of something minus the integral of something else, especially when it's between the same limits of integration, can just be written as the integral from a to b of the quantity f minus g dx. Like that. So that's the easiest way to think about it, because then you just have one integral instead of two. All right, so that's our task for today, is just finding the area between two different curves. So find the area of the region that's bounded by the graphs of y squared equals 3 minus x and y equals x minus 1. So the area that's bounded or enclosed by these two graphs is this area right in here. Is everybody okay with that? Okay, and then I want to, and it doesn't give me some limits of integration here, but I can, from those points of intersection, tell what those are. All right, so basically your formula for area is the integral of the top curve minus the bottom curve. That's another way to look at finding the area, and then from A to B. All right, however, if you look right here, your top curve is the line and the bottom curve is the parabola. But if you go over here, the top part is part of the parabola and the bottom part is part of the parabola. So in this case, we actually are going to have to break it up into two different integrals. So let's start with this first part right here. If I take the top curve minus the bottom curve, then the top curve is the line, which is x minus 1. I'm going to do this part right here. Yeah. I've got to break it up because basically the formula is the top curve minus the bottom curve. But for part of the region, I have one thing for a top curve and something for a bottom curve. But for the other part of the region, that top curve is something different. So I'm forced to break it up. Well, you break it up where those top curves change equations, basically. Okay, so let's try the blue one right here, the blue area right here. So the top curve is the x minus 1. What's the bottom curve? The whole parabola is y squared equals 3 minus x. But if we wanted to graph this on our calculator, we'd have to solve for y. And so we'd have to take the square root of both sides. Now, when you take the square root of both sides, what do you always have to remember? Plus or minus. So the top part of that parabola is the positive square root of 3 minus x. And the bottom part of that parabola is the negative part of square root of 3 minus x. So for the shaded blue region, my top curve is the x minus 1. The bottom curve is negative square root of 3 minus x. Now, what would my limits of integration be? I want to go the furthest left x value to the furthest right x value. Good, negative 1 to 2. This right here, this integral, just represents the area of the blue region. I should not have shaded that other part in yellow because that's hard to see. So I'm going to use purple for the yellow. Okay. For the purple, the area of this region is going to be the top part minus the bottom part. The top part, what's the equation? the positive square root of 3 minus x. Minus, and then the bottom curve is negative square root of 3 minus x. And obviously that minus and negative in both places becomes positive. Okay, now my purple region is between which two x values? 2 and 3. When you type this into your calculator, you should get 9/2. Okay, is the part in question like kind of this part right here? Or just the triangle? Okay, just the triangle right here. All right, right there, when you take the line, the integral of the line is going to be the area of that triangle. Okay, but then you're subtracting the integral of this right here, which is going to be the area from the x-axis to this right here. But when you, because it's below the x-axis, it's negative, but when you subtract that, subtracting a negative becomes a positive. Okay? So like this region right here, I'm going to call the line F, and I'm going to call the bottom part of the parabola G. So when you integrate F minus G, that's giving you the area between the two curves. But for this little section right in here, when you integrate F, the integral of F is actually going to be this little triangle right here, but it's going to be negative because it's below the x-axis. So you're going to get the negative of that little triangle. And then when you integrate G, you're going to get the entire area between the x-axis and G. But it's also going to be negative. So you're taking this little negative area and subtracting this whole big negative area, or I don't really like to call it negative area, but it's a negative number. You're taking this little negative number and then subtracting a bigger negative number, which that minus a negative becomes a positive. So that's why you just get a positive area between the two curves. Now, there's an easier way to do this problem. I know you hate it when I do that. We could also, and basically when we find these areas, when we found this area, what we were doing was we were finding an infinite number of rectangles, the areas of an infinite number of rectangles as their width approached 0. That's what integration is. And all of these rectangles were vertical rectangles where the width was x, or dx, and that's why we integrated with respect to x. If I were to draw horizontal rectangles, and add up the area of all of those horizontal rectangles, I'll get the same thing. But when I do a horizontal rectangle, the width of that rectangle is delta y, or in terms of integration, it's going to be dy. So now I have to integrate with respect to y. And instead of doing top minus bottom curve, I'm actually going to do the integral of the right curve minus the left curve, because that would give me the length of that rectangle. Does that make sense? Okay, the length of that rectangle would be the right side of that rectangle minus the left side of that rectangle. All right, but if I'm integrating with respect to y, then my equations have to be in terms of y. So I need to solve both of my equations for x. It will be easy, I promise. This first couple of problems are completely new to you, but you will think that this is the easiest thing that we've done all year soon. All right, so solve both of these equations for x. So the first one would be x equals 3 minus y squared. And the second one would be x equals y plus 1. Thank you. All right, so the right side is this parabola, what's the equation of the parabola after I've solved for x? 3 minus y squared. And the left side is the line, which is y plus 1. Make sure you put that y plus 1 in parentheses because you're subtracting that entire quantity. dy. Now, since I'm integrating with respect to y, my limits of integration need to be y values. So what do you think I'm going to integrate between? -2 and 1. The smallest y value is -2, and the biggest y value is 1. Now, when you type that into your calculator, you're welcome to use y on your home screen if you want, as long as you don't have anything solved or stored in y. Personally, I would probably just use x on your calculator. Either way, you will also get 9/2, which makes sense because it is the exact same area. Right. If you can deal with solving for x, that, in my opinion, is a heck of a lot easier. It all has to do with how many different rectangles you need to draw to represent all of the rectangles that you would add up to find that area. All right, at the bottom of this page, it kind of summarizes what we just did. For vertical rectangles, you're going to take the top curve minus the bottom curve because the height of that rectangle would be the top minus the bottom. And then you're integrating with respect to x because that's the width of the rectangle. And then for horizontal rectangles, you're going to take the right side minus the left side because that would represent the length of the rectangle. All right, we're going to do the first 3 together in class, and then the rest of this is going to be your homework. For each of the problems, I want you to sketch the region that's enclosed by the curves, decide whether to integrate with respect to x or y, so whether to use horizontal or vertical rectangles. Draw your typical approximating rectangle. By that, really numbers 2 and 3 kind of go together because if you're going to integrate with respect to x, you're going to draw a vertical rectangle. If you're going to integrate with respect to y, you'll draw a horizontal one. And then you're going to find the area of the region. Okay, so the first thing I need to do is find the region that's bounded by all of these curves. I will let you use your calculator for the most part to draw them. However, on this one, we should be able to do this without a calculator. So let's try to draw these without a calculator. All right, y equals x plus 1. That's a line. What's the y-intercept? What's the slope? 1. Okay. Y equals 9 minus x squared. What's the parent function? It's a parabola. What are the transformations? Up 9, and it's opening downward, right? All right, for a parabola that just has x squared or negative x squared, or 1 or negative 1 as a coefficient in front of the x squared, if you go down 1, you'll go right 1 on either side from the vertex. Over 2 and down 4, sorry. Over 2 and down 4. 1, 2, 3, 4. And then if you, or you can just plug in numbers. Or if you go over 3, you'd go down 9. Whoa. All right, x equals negative 1. What type of line is that? It's a vertical line. And x equals 2 is also a vertical line. Oops. All right, so I would like you to lightly shade the region that's enclosed by all 4 of those graphs. And sometimes that's the hardest part, is finding the region that's enclosed by all 4 of those graphs.